So hi guys, in this video, we're going to look at some sequential logic concepts. Albeit we've been able to conceptually introduce sequential logic circuits, cover SR flip, SR latch, and the gated SR latch. Now we're about to get into where things will get really interesting. So before we get to that, there are concepts I would like to introduce standalone in a video like this, where it's purely understanding the theory behind why things are the way they are, so that once we step into the world of flip-flops, step into the world of automated times digital signals, it's no longer such a big thing to handle. All right, so let's get on with it. The clock pulse stroke signal. Recall in the last video when we covered the gated latch. Okay, so we had an AND gate paired with another AND gate. This could be my R, this could be my S, this could be my enable. This goes to my not OR. This comes to my not OR. Okay, and this is fed into this, and this is fed into this, which is really, pardon the roughness of the diagram, which really makes sense. But the issue we had with this, remember why we said we needed an enable? We need to be able to control when things happen. Okay, be able to control when things happen. Without an enable, any change in the states of either R or S would affect our output Q. Okay, but we needed a control. So now the issue comes when we want a regular output. Okay, so what if I wanted my output to be 110, 110, 110, 110, 110, and there was 100 milliseconds between these two. Okay, with the enable pin, the idea is that you pressing down on the enable button. Okay, it could be up, it could be down. So pressing down on the enable button, okay, click. So this could be 1, this could be 0. So pressing the enable button, you physically controlling it, is what activates the enable. But you run into a problem when you need very tiny but periodic signals, and that's where the clock pulse comes in. Okay, so you sort of have to imagine a classroom. Okay, let's say we're in a hall and in a lecture, and we don't have a means of measuring time. If the teacher says, or if the prof says that the assignment is due today, if the professor says that the time is due this afternoon, well, me and you definitely could have different understandings of afternoon. I could submit my assignment by 4 as beta by 4 p.m. and claim it's the afternoon. You could submit by 12:01, claim it's afternoon, and a good friend of mine could submit by 2:23 and claim it's afternoon, and they won't be wrong. So we sort of need an external clock signal, which you can say is why we have clocks in most classes, right? So that we can get an albeit universal idea of what time is. So that is what the clock signal is. So it looks something like very nice. Okay, high, low, high, low, high, low, high, low, high, low, and so on and so forth. Okay, if you remember your binary, the low is a 0 and our high is a binary value of 1. Okay, so this is going to go on forever. Okay, for a very long time as you increase in time, forever. So that's the idea of the clock pulse, right? So you increase in time, you go from 0 to 1, 0 to 1, 0 to 1. And the advantage of this is that the time space between these two is always going to be uniform. Okay, it's always going to be uniform. So recall we said that if we wanted to change things every 100 milliseconds, then we could make the distance between high pulses 100 milliseconds, controlling this electronically. So it's a very huge advantage of clock signals. So now, if we want to make our outputs, so let's say 1011, 1011, 1011, 1011, and want a constant space between 1 and 0, 1 and 0, 1 and 0, 1 and 0. Instead of having a really unfortunate guy sitting at the enable button and hoping he does a good job of pressing it at the right time, okay, we could just introduce a digital clock pulse. So you could call this a clock It's a clock pulse, a clock signal. Literally speaking, this is a square wave, okay? So for most purposes, it's cool. It's ideal to assume that jump from 0 to 1 is instantaneous, okay? So as we carry on, you're just going to assume that to make your solving easier. So that's why we need a clock pulse. You need an external step, an external governor over when things happen, okay? So it turns out that in controlling things, we're even going to need more than a clock pulse. We're going to need to determine what the clock pulse does specifically to change our circuits. So now, why we're going to get into the topic, why do we need edges? So we're able to introduce the clock pulse, okay? CLOCK. We've been able to introduce the clock pulse. So now, why do we need edges? Okay, these type of edges, sadly, are the ones relating to digital electronics, not particularly of hair. So why do we need edges? The reason we need edges is because there are two ways to make your clock affect something. So if I were to draw the clock pulse again, up, down, up, down, up, down, up, down, high, low, etc., like so. Okay, so this is 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, like so. So you can see why it's so. Remember we said that this 0 is low and 1 is high. So physically we can actually see why it's this way. So there's two ways to make our clock pulse affect something. Okay, we can look at it, say when my clock is high. So you can say when my clock is 1, when clock is 1, then change something. Okay, when my clock is 1, change something, which means that for the duration that this clock is 1, that means I'm going to have a certain output being affected. For duration this is 1, I have a certain output being affected. For duration this is 1, I have a certain output being affected. But you run into a problem when you're dealing with this, okay? So this is called level triggering, which means that for the level is 1, so is level triggered for 1, or it's high, or it's a high level triggered, okay? Because so far as our value is high, things are changing. So remember, level trigger means I'm changing with the level of my clock pulse. My clock can either be 1 or 0. If I'm level triggering, I'm changing when my clock is either 1 or when it's either 0. So that's up to you or the question to decide. But the problem with this is that we get a change throughout an entire period. Okay? Is that we get a change throughout an entire period. What does this mean? Which means that for the entire, so let's say this is 250 milliseconds long. So for the entire duration that this is high, I'm going to have a change in my circuit as really fast as possible, because a lot of changes could happen in that time. So for the duration this is 1, this is going to change a lot in that period, which is sort of not what we expect, because we're going to have a lot of switching back and forth, which is going to eventually affect our circuit. So that's one way to look at it, level triggering. But the better way, the more precise, economical, engineering way to sort of do this is to make it edge triggering. So this is why we need edges to make an edge trigger. Okay, so we call level triggering. Level trig is for 0 and 1. Then edge trigger only triggers things when there is a change. Okay, and you see that makes more sense. So the active trigger, okay, so being active edge triggered or positive edge triggered. Okay, we can call this positive. Okay, so positive edge triggering. Positive edge triggering which means that whenever I'm changing from a 0 to a 1, affects my circuits. Negative edge triggering means that whenever I'm changing from a 1 to a 0, affects my circuits. Okay? So what does this mean? So now instead of changing for the entire duration that this is high or that it is low, okay, now get the really cool advantage of only changing at one particular instance. Okay, so here in this case, I'm going from a 0 to 1, which means I'm going to have changed my circuit here. In this case, I'm going from a 0 to a 1. I'm going to change my circuit at this instance. I'm going from 0 to 1, changing my circuit at this point. I'm going from 0 to 1, changing my circuit at the instant where that happens. Okay, so that's the advantage we come into when we deal with edge triggering. Instead of keeping something on and changing for a really long period of time, things affect over one particular instance. Okay, so it's sort of the way you really don't want your alarm to be your phone to be ringing for the entire duration you're on a call, but you like your phone to notify you when you're going from no call to a call. Okay, so things are really better when you move from edges. When I'm changing from so to so, why let this affect something? When I'm doing a race, right? I say when people are running, we're doing a race. You usually don't run for the entire duration that the race is alive, right? You run at the edge when the whistle is being blown. So here there's no whistle, and here there's whistle. Okay, and that's when you start running. And the finish line too is also a trigger because you're running before the finish line and you stop running after the finish line. So most things you handle in life and in electronics are going to be edge triggered because it makes more sense, it's better. You get better electronics, smarter electronics, faster electronics when you deal with things that way. Okay, so I've covered triggering, why we need the certain types of triggering, the active triggering and the positive trigger, positive edge trigger and the negative edge trigger. So the last thing we're now going to handle is the toggle. Remember the first thing we introduced was the clock pulse. Okay, high, low, high, low, high, low, high, low, high, low, da da da, boom, pa. This the clock pulse was the first thing we introduced. Then the next thing we introduced was the type of trigger we were using. Okay, for the entire duration is on, so this is 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 0. So we agree that we're going to be using edge triggering for most of this, since it gives us a better way to make things happen over a particular instance so that we can look at the states before events and after the trigger events. Okay, usually an interrupt. So before this interrupt of 0 changing to 1, what happens? After this interrupt, what happens? That's positive edge triggering. The negative edge triggering is the analog of that. Okay, which means that when I'm dropping from a 1 to a 0, what happens? When I'm dropping from a 1 to a 0, what happens? When I'm dropping from a 1 to a 0, what happens? Okay, so that's what happens when we're dealing with the type of triggering. So the last thing we're now going to cover is the toggle. The toggle is a characteristic of certain sequential circuits, which means that if my state at qt is 0, my state at q t plus 1 is going to be 1. My state at q t plus 2 is going to be 0. My state at q t plus 3 is going to be 1. So it's also it's a really funny thing. It means bound to toggle between inputs. Change a 0 to a 1, change a 1 to a 0. In the introduction to sequential logic circuits, I covered an example that sort of gave a really good idea of that. So I'll link that at the top. So if my input, if we were toggling with the active edge trigger, okay, which means that I'll first of all point out every region when I'm changing from a 0 to a 1. Okay, that's wrong. So this particular one is a 4. Okay, from a 0 to a 1. Okay, 0 to 1, 0 to 1. Okay, so if in this state I was 0, at the point of this interrupt, I'm going to toggle to 1. By the next interrupt, I'm going to toggle to 0. I'm going to be 0 for the entire duty cycle, the entire duration, the entire full 360 degrees high and low of this, right? Because the sine is the full 360 degree phase. Okay? To 1, to 0, to 1, to 0, and bringing this down to 1. So that's what it means to toggle. The same thing will happen if we started with the 1. By the interrupt, it will be 0. The next interrupt, as the positive edge trigger, to be 1. The next interrupt is to be 0, 1, etc. Pardon me, 0, etc., etc. So these are the very, very basic introductory concepts we have to cover when dealing with sequential logic circuits. We've covered clock pulses, level triggering, edge triggering, the types, and then finally what it means to toggle. Since most flip-flops are very, very useful for creating toggle circuits. So in the next video, we'll enter flip-flops, get into different types of flip-flops, why it matters, why they differ from latches, and then get more advanced as we continue on with digital electronics. So thank you for watching. I'll see you in the next video.